Hey everybody, I'm going to be spamming meta interview questions for the next 45 minutes before I go live on Advent of Code. Let's see, YouTube. So I'm going live on Advent of Code around, where is this playlist? Going live right now. What's the current time? 8:43. So yeah, me and my brother are going to be going live for day 10 in 61 minutes. So I'm going to spend the next 45 minutes spamming meta questions just to prepare for this Advent of Code. Let's get into it. Given the root of a binary tree, determine if it is a complete binary tree. In a complete binary tree, every level except possibly the last is completely filled, and all nodes in the last level are as far left as possible. It can have between 1 and 2 H nodes, inclusive at the last level. So this is a complete binary tree. I know what a complete binary tree is because that's the main data structure used for heaps. Well, the data structure is tree, but it has to follow a complete, it has to be a complete binary tree to be for good use on a heap. And yeah, let's just get straight into actually coding this up. Right before this, I was like investigating how I would solve this, and I think how I'm going to solve this is probably like, let's see. So this one example, that's actually a complete binary tree. So what I'm thinking is, what we do is we label each node, and if it's a complete binary tree, when we do a breadth first search, it's going to be like monotonically increasing by 1. It's going from 0, 1, 2, 3, 4, 5. And if there's one here, it would be 6. And it would never go from 0, 1, 2, 3, 4, 5, supposed to be 6. So if we did a BFS here, you'd see a jump a number, and we'll know automatically that it's not a valid binary tree. So how we would do this is, so we know automatically it's not a valid binary tree or valid complete binary tree. So how we do this is like, this is just a property that I learned from a heap, but basically, if you use the to calculate the left and right neighbor and assign it the correct index, because a lot of times when you're working with heaps, you're working with a array. So you need to find what index, like where the left and right indexes are supposed to be. So the equation for that is pretty much the left index is equal to 2n, and the right index is equal to, or 2n plus 1, and the right index is equal to 2n plus 2. So if we start off with knowing that the top element has a n equals to 0, then when we push its left child, we do 2n, 2 times 0 plus 1, that equals 1. And what do we have here on the right side? Oh, sorry, this should be 2n plus 2. So 2n plus 2, what's that? 2 times n, if n is 0, plus 2 equals 2, right? So now we're probably like giving numbers to these, and then we're here. What's 2? The left child here, 2 times 2 plus 1. Or sorry, it's supposed to be 1 here. What's 2 times 1 plus, 2 times 1 plus 1, that equals 3. The right child, 2 times 1 plus 2 equals 4. Then we have this left child, right? Or this node here, node number 2. 2 times 2 plus 1 should equal 5. But since it's not there, we don't really pop it into the array. So right now we'll have like a result array of like 1, 0, 2, 3, 4, and finally 3, and we pop the right child. What's 2 times 2 plus 2 equals 6? And now we'll see that there's a jump here, and it's false. That's not a perfect binary tree. So I think, how I understood this, how I understood what to do here is just because I've like built a heap from scratch before. So I know that like, in order to satisfy the complete binary tree property, pretty much you should be able to assign indices to all of the different nodes, because usually these indices actually map to indices in some sort of array that where you store the heap, because the heap is usually implemented, or the easiest way to implement it is using an array. So let's just implement this and see how it goes. So we start with a default dictionary right here, and what we're gonna do is do like a breadth first search. So if root is none, capture this base case, return true. So if the root is none, return true, because that is a complete binary tree. Otherwise, we have a queue, and we start a default dict. Oh no, we don't want a default dict here. We want to use a dequeue. Queue. So we start with a dequeue, and we start with the root element, and we assign that the letter 0 or the number 0. Now, then we will say like last seen equals 0, or we'll start with -1, and then we'll return true if we're able to actually do a full breadth first search. If we're able to do a full breadth first search and not return, if we're able to do a full breadth first search and not see the error case, which is like a jump in the numbers that is not monotonically like just 1. So we'll say while the length of the queue is greater than 0, what are we going to do? We're going to say, we're going to take the node, and we're going to take the value, and we're going to do queue dot pop left. That gets the first element of the queue out. And what we're going to say is if the value is not equal to, if value -1 is not equal to last seen, return false, because we should just be 1 greater than it. And then we'll say last seen equals that value, because if it is true, then we need to replace the last seen. So it's like increasing. Then we'll go, pretty much we'll go, yeah, we could probably even check that each one kind of has a, yeah. I mean, we'll go with this. I think this works. So what we're going to do is like if node dot left, then what we're going to do is queue dot append. We're going to append the current value to 2 times value plus 1. Is that we said the equation was? 2 times value plus 1. Cool. Q dot append 2 times value plus 1. That's the but don't dot left here. So we're pushing node dot left onto the queue, but we're also saying that the value of node dot left, or like the unique label that we're giving it, is 2 to the or 2 times val plus 1. And then because that's what we said right here. And then we take node dot right, q dot append right plus 2. Cool. See if that works. From collections, cannot import dequeue from collections. Collections. Oh, sorry, I spelled it wrong. EQ, that. It's a weird name. While the length of the queue typo. Nice. See if that submits out. Cool. Looks like it worked. What's the answer? So in every level except possibly the last is completely filled, and all nodes in the last level are as far left as breadth first search approach. What is this? Okay, they're doing what we did here. What did we do here? We did a depth first search approach, and they did the breadth first search approach. Level order traversal. Yeah, I don't even know what they're doing here. My approach worked though, so I'm just gonna go with that. Whatever. I don't even get their solutions there. So, oh shoot. Let's go with this add number. You're given two non-empty linked lists representing two non-negative integers. These digits are stored in reverse order, and each of their nodes contain a single digit. Add the two numbers and return the sum as a linked list. So 7. You may assume the two numbers do not contain any leading 0. So we have to build a linked list and create that. Let me think. So you're given two non-empty linked lists representing two non-negative integers. So it's giving us the reverse order. Add the two numbers and return the sum as a linked list. So 2 plus 5 equals 7. 4 plus 6 equals 0. 3 plus 4 equals 10, and then you carry 1 over. Nice. And then you carry 1 over. And then return the sum as a linked list. Okay. That makes sense. What is this number? So I think what I want to do here is we're given the linked list. Where's closest binary search tree value? Interesting. So giving list 1 and list 2, right? What we're going to do is like probably put a pointer at the start of 1, and then we're just going to traverse. So we're gonna take these two, and then we're gonna build a linked list. The linked list is going to be like, what are we gonna do with the linked list? The linked list is gonna be when we put 9 times plus 9. We're gonna create a node called 0, and we're gonna keep some variable called carry. So we'll have like a variable called carry somewhere else. Right now, 9, we move over this element and we do 9 plus 9 equals 9 plus 9 here. How does it work? Oh yeah, that's equal 18. Sorry, confused myself. That equals 18, and then we carry over 1. What's 9 plus 9 again? 18 plus 1 equals 9. So we'll add another node, 9. And it still has that same carryover. 9 plus 9 equals 18. Gives us 9 again. Sorry, let's move this over. Gives us 9 again. So we keep in the same carryover. 9 plus 9 again equals 18 plus 1 carryover equals 9 again. but now one of the lists opens. So maybe when one of the lists is ended, I'm just gonna like have some default that will assign 0 there. So what do we get here? 1 plus 0 equals 10. So 9 plus 0 plus 1 equals 10. So we get 0 here. Let me move this over. Probably shrink it a bit. 9 plus 0 plus 10. We still have the carryover. So now what do we have here? What's 9 plus 0 plus 1? We get another 0 right here. Carry over 1. And then we probably get another 0 right here. And then finally, since if we have another carryover, we just attach like a 1 more there. What's the answer to this? 89990001. 89990001. Okay, cool. I think, and then we just need to build that linked list, and then we just return that linked list. So I think one of the easiest things to do when you're using a linked list is it is guaranteed that the list represents a number that does not have leading zeros. Okay, that's fine. 44% success rate. Interesting. So 0 plus 0, you should return 0. Okay. So usually working with linked lists, the one thing you need to watch out for is like the cases that are like the edge cases, like the end cases. So a lot of times we use a Sentinel node in order to make it easier to build. Sent node equals list node, right? So that's at the end, we're going to do sent node return, because we need to return a Sentinel node at the end. Where are we? Yeah. So we're going to return sent node dot next. So we're gonna keep this going, like if left dot if left dot if left is none, or sorry, L1, and L2 is none, return none. Catch those cases, and we're gonna say while left, while, so we're gonna say L1 equals pretty much just L1, right? Or yeah, we can kind of reuse this variable. We'll say while L1 or L2. That might be bad practice to modify the parameters, but L1 pointer equals L1. L2 pointer equals L2. I will say while L1 pointer or L2 pointer, because we want to traverse, we want to keep traversing even if one of them is already at the end. So we're going to say left L1 value equals 0 if L1 pointer is none, else L1 pointer dot value. Let's do the same thing with L2. L2. So we have an L2 value here. If L2, okay, is none, cool. Then we're going to maintain some sort of carry. Right? And then let's just say current node equals Sentinel node, right? Because we want to know what current node is, like the current node that we're on. Like the last node, basically the last node we built. So adding two. I'm adding two numbers using linked list. If L1 pointer is none and L1 pointer value, we'll do the sum or next node value equals L1 val plus L2 val plus carry, right? Then what I'll say is carry equals next node val. So we do mod 10 or divided by 10? Mod 10. Because if it's like 11, we get 1. No, but if it's 12, carry equals if next, we'll do if next node val is greater than or equal to 10. We have a carry, else the carry equals 0. Solving this linked list question. So this will be the next carry.
You're trying to cook. Are you trying to cook yourself before the advent of code?
No. I'm only doing 23 more minutes of this, but I already did one question. What are these guys talking about? Super insightful. Oh, cool. One of my old videos is just getting views now.
Nice.
It's getting hit by the algo.
Nice. Yeah, you gotta say what's up to those subscribers.
So what we have is we're grabbing the value of L1 and L2. And then we take that and then we add the carry to it. And then what we're going to do is like the new node is equal to list node. List node. The new node is equal to list node. List node where, what's it called? We're going to give it this next node value. And now we're going to worry about like what happens after. So will there be another carry? Depends. If the value is greater or equal to 10, yes, the carry will continue. Otherwise, the carry will be 0. Then we're going to then we need to move over our current node. But we're going to say our current node dot next equals current dot node dot next equals this next node we just created. Then we have to move forward our pointer. Current node equals current node dot next. That moves us up. So we say current node dot next equals the new node. So now we basically create like we have our sentinel node, right? But then we basically create like this 8 here. And then our current node is the sentinel node, but we move it up here. Now we take if L1 pointer, then we do L1 pointer dot next equals L1 pointer dot next. Are you hitting the gym? Or are you gonna chill today? L2 pointer equals L2 pointer dot next. I think that will get us, and then we just have to handle this carry case. If the carry equals 1 still at the end, if the carry equals still 1 at the end, we'll just have to create this new node like this, where the list node value is 1. Then we'll take the current node dot next equals this new node. So I'm just going through this fast, mostly because advent of code is starting soon. So what happened here? So the value should be mod 10. The next node. Where is this value? mod 10 so we don't go over. 710 mod 9. Oh shoot. So 10 mod 9 equals 1. No. 10 mod 10. What's 10 mod 10? Is that equal 0? Should be. Okay. Ten mod 10 next node val, or let's calculate the carry here, or let's do so why did that equal 10? Next node val, so we say print the next node value right here, 710 that, and then we do mod 10. Does that not work? Oh, there's something weird with the brackets there. Looks like it doesn't follow like bedmass or something. That's crazy. I did not know that. Boom. So how much space is that gonna take? Do they want us to do it faster? How much space? O of 1, O of 1, O of 1. I think I did the whole thing in O1 space. Yeah. Pretty much did the whole thing in O of 1 space, kind of. Is that true? Well, no, I'm creating space. But let's see what they say. Oh, they're not counting it either. But looks like they have the same algo as me. Cool. Yeah, but I guess they simplified that carry portion. But yeah, they use the Sentinel node 2. They have a current. They have a carry. But they like rearranged the parameters, which I didn't want to do. But yeah, looks good to me. Maybe we'll have time for one more. Let's do, what's the current time? 9:11. I have 16 more minutes. So let's just do couple easy ones. But closest binary search tree value. Given the root of a binary search tree and a target value, return the value in the BST that is closest to the target. If there are multiple answers, print the smallest one out of all of them. So for example, okay. So if we're looking for 3, oh, why say I don't want any solution? Don't want any solutions here. Create hello function. Why is this only in JavaScript and TypeScript? Interesting. I know JavaScript too, so I don't even know. That's kind of a weird question. What is this? Okay, how do we do that? Let's just think about it real quick. So we have this binary search tree. The property of a binary search tree is pretty much that like all values to the left of a node are smaller than it. All values to the right are smaller than it recursively. So you can see if this is 4, all values here are smaller than 4. And then all values to the right is strictly greater than 4 as well. Strictly, I don't know if that's the case, but it should be like all less than. So if that helps us with finding. Pretend we're looking for 3 or something. Then we know that we don't even have to search this right side because the number here is 4. So we know that since all the elements to the right in the right subtree are larger than 4, we won't find 3 there, and we have to look left. That allows us to like easily search this tree really fast. So how are we going to do that? I think what we need to do is we just search for the target value. And while we're searching for the target value, we're just looking for the element that's closest. We're just looking for an element that's closest to the number that we want to find. So pretend if it's 3, right? We like store our result equals to 4 because that's the closest one to 3 so far. Then we like move down to 2. 2 is actually as close as 3, but it's a smaller number. So we can add a result to 2. And then pretend if 3 wasn't here, right? This would be our closest answer. But pretend there was like a 2.5. What we'll do is, yeah, we'll look in the right side because all the ones are less than 2, so we don't need to look. Or if we're looking for, because yeah, we're looking for 2, 3. All of them are less than 2 on my left side, so I know I'm closer than any of it. So let me try the right side. So we see the right side, and 2.5 is closer than 3, so we store that value as well. So I think that's pretty much all we have to do. Pretty much traverse the tree and keep a count of which one's the closest to that value. We'll probably do that using like a, like we don't even need a, we could do that with like ov1 space actually. Let me try to think of how we're gonna do that. We can do that for, we can do like our start node. What are the constraints? The number of the nodes in the tree is in the range 1 to 10. So there's always at least one. No, there's always one node in the graph. So cool. So the closest it's given, return the value in the BST is closest if there are multiple answers. So yeah, let's start with like result equals root dot value. Current node equals root. Then we'll say return the result. And then we'll just be like, while the current node actually exists, what we're going to say is like, we're going to try to, if, let's see, we're going to do result equals, so we start with the root. So we'll say if, or we'll let's keep track closest. We'll say we need to be like get distance. There's gonna be an ov1 function, get distance from num self num1 num2, and it will return the absolute value of nums1 minus nums2. So that returns us the absolute value between two numbers, and that's the distance. So we'll say if the get distance of the current node dot val from the target is less than like the current result, say get distance from the, we'll say is less than the distance from the closest found and the target, less than equal to, because if it's equal to, if it's less than or equal to, and the current node dot val is less than, and it's a smaller value. Where is it? Okay, and the current value is less than closest found. What we're going to do is we're going to update closest found equal to, so now the closest found is actually, what's the closest found? Yeah, would actually be the current node dot value. Because if it's less than or equal to, and that, because we also capture the less than. So if they're the same distance, or this one's even less than, and the current value is less than the closest found, we update the closest found to, okay, cool. And then basically, if the current node dot val equals the target, we kind of just return the target. This is like kind of like a regular binary search thing. So lf the current node dot, if the current node dot val, if the target is less than or equal to, is less than the current, are these unique nodes? What's the property of a binary search tree? I think if the target is less than or equal, or if it's equal, then we're good. But if the target is less than the current node, then we need to look, the next current node is equal to current node dot left. Else current node equals current node dot right. So yeah, let's run this code. I think that works. Hopefully that works. One. Hopefully that works. Cool. Let's freestyle. What? Output target 3.4 to expected to got 1. What does it look like? 1, 2. If the get distance is less than or equal to, why didn't that case work? Let's just run through our code quickly. See, what's the time before advent of code? 20 more minutes till advent of code before I have to go live. So let's just like look at it. Let's analyze this test case quick. Visualize it. So if the target is 3.41, right? We start off with the closest value is 1. So if the distance between 1 or 2 is less than, okay, less than or equal to. Okay, we'll just have a couple case here. If, or we'll say this from current, dist from best. So if the distance from current is less than equal to distance from best, we're gonna have to like calculate some stuff. Right? We're gonna, if the distance from, if they're the same, if they're actually the same, then we just return the closest found is actually like the smaller one. So we'll just say closest found equals the min of this, that. If they're equal. Else else what we're going to do is we're going to grab the one that's closer. Distance from current is less than equal. If they're equal, then that. Otherwise, yeah, let's just do this. Elif. Kind of confusing. So we'll do like this. If the distance from current is less than the distance from the best, that's going to be our new closest found. Closest found equals current node dot val. Or are we supposed to return root? Oh, this is rough. How am I flopping this easy question? Output is 1, but not equal to. If let's just do here. Why am I printing here? What I want to do is track. Oh, I'm not even calculating. Put this outside. Should work. What? Does that even work? What kind of edge case is that? That's such a weird edge case. That's terrible edge case. Okay, wait. Note that val is less than equal. Is that even correct? I bet people are complaining of this one. This one comes with a bug. It looks like... What? Let's just see if this passes. This doesn't even make sense. Why, like, just that edge case? Why is it like if the target is 2.0, the closest thing or the result should be return 2.0? Oh, I'm returning a float? That was complaining about? What am I complaining? How am I returning a float? Oh. Okay, wait. I'm gonna finish this up. Plus node equal int. Oh, interesting. Oh, because they passed in. That's kind of annoying. Boom. Okay. Solve that. People were saying that shouldn't have been an easy question. So let's see. O of 1 space. Binary search. O of H space. Yep. Cool. Pretty much right on time. I finished like 3 or 4 questions. Thank y'all. See you all in the next video. I'll be grinding out more FANG interview questions.